I just happened to have seen this video where some software engineer interviewer asked the question, what happens when you type a URL in a browser? And this guy said the response can be very revealing about the tech level of the person responding. Well, the interviewer gave his sample response and I thought it was lacking. But this is a really great question because if you understand all the pieces of this puzzle, you might actually understand where the privacy threats are. So I'm going to make a two-part video. This first part will just go through the technical details of what goes on after you type a URL in the URL bar of your browser and then you press enter. And in part 2 next week, I will then change it a little bit and go through a scenario where a person is privacy aware and modify this tech environment to see if this makes any difference. This will be truly educational, and I just bet that 99% of you will not know the deep details of what actually goes on. I'm guessing that interviewer can't go this deep either. Stay right there for a fun learning experience. Okay, I'll try not to go too deep. Fortunately, I will never get interviewed because I don't need a tech job. But if I get asked this question, I may not be given enough time to answer. So let's type on the URL bar of the browser. The effect of this is different, by the way, between mobile and a PC. Yup, just a little detail there. And I don't even care what the browser is. Let's say you type https www.example.com. Starting with the obvious, the browser communicates using an IP address, so www.example.com has to be converted to an IP address, and it asks the OS to translate that. The browser funnels the www.example.com domain to a domain name service resolver, which is set to listen on port 3. The DNS Resolver will see if this has been searched before, and if it is, the domain will be found in the DNS cache of the device. The idea here is that caching reduces the traffic for DNS requests, but after a time period, the DNS entry in the cache expires, and the OS then sends the request through the network to a DNS server. Now here's the trick. If you're on Android, the default now is that this request is sent to Google. It is labeled on Android as private DNS. Actually, it is an aggregated DNS because Google can see every website that you visit and no one ever checks this setting. The idea is that this DNS is private because communications with Google are sent using TLS encryption. But of course, no one mentions that it goes to Google. Google then receives other pieces of information with your request, such as your IP address. It then returns the IP address to you for www.example.com, which happens to be 93.184.216.34. Just to be clear, Google sees these DNS requests, finds the IP address of the source, and records the response. Thus, they know what websites have been requested by any particular IP address source. Now, if you turn off private DNS and set it to automatic, the default DNS provider is your ISP. Let's say you're on Verizon, then Verizon gets your IP address and your desired domain, and they get to store that. And this particular interaction is done in plain text, so it is readable not just by Verizon, but anyone else sniffing the network. And yes, you can change the DNS manually instead of relying on your ISP's DNS. But your ISP can do something called DNS Proxying, where they can ignore that you're sending your DNS to some other party, and they'll process the DNS request anyway. This way, they can still record every website you're visiting. Okay, now the browser has the IP address 93.184.216.34. The next thing to do is negotiate an encrypted channel with that website that we call www.example.com. It has to do this because you specified HTTPS on the URL. If you didn't, it would skip this step and all traffic would be visible as plain text. Your browser will then use the public key of the website to send an encrypted message to the web server saying it wants to initiate a session, and it will pass a unique generated key that is known to your browser. This encrypted request and all other requests will be sent to the server on the server's port 443, since this is HTTPS. HTTP uses port 80. The web server will be able to decrypt the encrypted message because they have the private key for their openly seen public key. An encrypted response will then be sent to the browser using the browser's generated key. And the conversation then continues with the same key for both sides. This key is used to do AES-256 encryption, serving as a symmetric key. Symmetric key means the same key for both sides. The little interesting tidbit here is that a web session starts out exchanging keys using asymmetric encryption, but actually continues using symmetric encryption. This AES-256 encryption key is renegotiated at regular intervals, so they have a key that is always changing. Sounds pretty secure? Well, it would be, but only as long as you trust that no one else has the domain private key. But as it turns out, you have to trust that someone didn't keep a copy of the private key and then distributed it, or that someone is not spoofing the domain with a completely different set of public and private keys. Now, the web server translates the encrypted request of the browser into plain text and executes the code on the server. The return text is formatted in something called HTML, which the browser can display. This is how browsers want to see the return traffic. Some details that are not clear here. You cannot hide that your IP address is talking to the domain www.example.com, even when using HTTPS. This is part of the message that cannot be encrypted. This is visible to all third parties watching the network. However, other than the fact that your browser is seen communicating with www.example.com on port 443, no other details of the conversation can be seen, although the amount of traffic can be seen. Okay, lots of missing steps here. For every request to the web server, each browser must pass a lot of information to the server. First, all traffic is accompanied by the IP address of the sender. Well, this is no mystery, since every Ethernet packet on the internet always has the IP address of the sender and the receiver. Now, this part is not obvious to non-programmers, but part of the HTTP request is a block of information about the sender called the UserAgent. And here's some example UserAgents. The UserAgent identifies the device of the browser. Back in the day, this was used by programmers to determine the type of display used and capability of the mobile device, so the website can size the display to fit the screen. Unfortunately, this UserAgent is also part of identifying characteristics of the sender, which can be used to fingerprint the user. All devices emit a UserAgent. The UserAgent is formatted by the browser, but it is taken from the OS, and thus it cannot be modified by the user directly. Now, the web server can execute code on the browser using a scripting language called JavaScript. So let's make sure this is clear. The server triggers the JavaScript, not the client. So the server not only receives information like a UserAgent, it can also run code inside the browser to not only format the displayed content and react to user input, but also to query the device. For example, the web server can read cookie files on the browser device and query details about the machine and the browser, which are once again important for something called browser fingerprinting. The web server any web server actually, can then find sufficient information to identify a unique user just by how they set up their particular browser, and also the kind of device being used. Plus some other details like time zones, IP addresses, and locations. In many cases, this information is enough to pinpoint specific individuals to recognize that your device has been seen before. And the web server can respond accordingly, for example, by recording your activities in a profile or presenting you with options relevant to what you've done before. Now let's get Google specific here. Google will ask you to log in using your Google ID on your browser. Or if you have an Android, it already knows your Google ID because it was part of the phone setup. The Google ID is of course your Gmail address, and it will be stored in multiple places on your device. But definitely it will be stored in a cookie. There are rules for how cookies are used. The basic rule is that cookies can only be read by the domain that created them. Meaning google.com cookies can only be read by google.com. This is a very specific restriction and is implemented on all browsers. This prevents third parties from scanning your browser cookies and retrieving other information like names and addresses and other content you typically fill on various other websites. But only two platforms can override this limitation. One is Google and the other one is Facebook. This is very interesting since, of course, Chrome is the most popular browser in the world and it is created by Google. In theory, since Google makes Chrome, Google could in fact override any limitations of reading restricted content on a device, but set aside that thought for now. As I said earlier, the Google ID is stored in a google.com cookie, and I also said that Google can override the limitation of reading cookies from other websites. Well, not exactly. What happens is that Google made a tool for analyzing web traffic, and it is called Google Analytics. So it sells the concept to all website developers that if they want to see their traffic stats, they need to include Google Analytics in their server code. Additionally, if they want to get advertising in their websites, they need to integrate Google Ads in their code and allocate space in their websites for these Google Ads. But what actually happens is that when you are asked to put Google Analytics or Google Ads in a website, what is being created is a website in another website. The technical term in HTML is called an iframe. This iframe can be invisible, or in the case of a Google ad, it can be a predetermined space. But the code to generate this iframe basically established a google.com website inside any website. And Google changes the actual content of this iframe using their own web server. The vast majority of all websites include Google Analytics and Google Ads. Thus, there is a google.com in all these websites. And as I said, google.com sees Google cookies. Thus, every website can track the Google ID, and then that is collected by Google. What this means is that Google can see pretty much every website you visit. It can already do that to the vast majority of devices using private DNS, which it controls. I didn't mention earlier, but Google also intercepts all URLs in Chrome and on an Android and passes it through something called Safety Net, again intercepting every URL in those devices. And on top of that, Google sees exactly what you're doing inside every website, including, by the way, knowing what you're clicking on the websites, because a Google iframe in HTML can interact with the main website or the main frame. This is how website owners can actually see in Google Analytics who their audience is. For example, the specific interests of the people who visit their site, their location, are visible to website owners. You can tell that your audience is photography enthusiasts, foodies, and sports enthusiasts, for example. But though they may not show it, Google also knows every person's political beliefs. And this can be provided because Google knows every individual that visits every website. Of course, Google limits what the website owner sees about their audience, so you are not able to drill down to individuals when looking at the analytics. But it should be obvious that Google is able to see this. And this, of course, is not understood by the majority of people. Google knows all. Now, Facebook has a similar mechanism for accessing cookies for Facebook.com. When you use Instagram, Facebook, or WhatsApp, these platforms can store any kind of data in a Facebook.com domain, for example. And then various websites are very happy to include buttons for a Facebook like button, which is another iframe, just like Google Analytics. And this enables Facebook to see what you're doing on the internet outside of Facebook. This is not dissimilar from what other websites can do if you do a Google login, Facebook login, or Apple login on some third-party site. That login is basically allowing that website to integrate code from that platform, and then that platform is able to track your activities on a third-party site. Now it goes beyond this. Devices like Google Androids and iPhones will have some Google app installed on it, and Google then is able to retrieve other identifiers on the phone. On the Android side, it is able to see things like the IMEI, IMSI, MAC addresses, ARP tables, phone numbers, IP addresses, advertising IDs. And it can obtain much of the same information from an iPhone. The kicker here is that the Google app or apps on a phone, let's say like YouTube, are able to send the Google ID and phone identifiers to Google itself. Typically, these mobile devices are also used for two-factor authentication, so the mobile device becomes a way to verify a fixed identity, an identity tied to hardware. Without even knowing a real name, Google has the ability to have a verified profile of everything you do on the internet and have it tied to a Google ID and a specific mobile device. Also, because the mobile device is mobile, it can be used to verify your location even as you're using a browser on a computer without location enabled. All Google has to do is verify where your mobile device is that is using the same Google ID. You can easily verify that they are aware of all these devices in Google security. This is such a rabbit hole actually because there's so much more. For example, any website can request your location again by running JavaScript on your browser. This then triggers Wi-Fi triangulation, which pinpoint a location without the use of GPS using any Wi-Fi equipped device. And it is Google that provides the code for Wi-Fi triangulation. And this is not even necessary now since a device running Google Android can be located at all times. And since the Google ID can be matched to the mobile device, your actual location can be always known. So this is what actually happens when you type a URL at the browser. It's a lot, isn't it? And it has gotten so complicated. There's actually more and tied to other applications running at the phone end, but I'm limiting this to those things directly connected to typing at a URL bar. In the next video, I will talk about this same scenario, but using various techniques that will defeat the tracking that is possible here by Google. Folks, I have privacy products that protect your data so it will not be exposed to any rogue app. We have a Brax2 privacy phone running an open source Brax OS that makes your phone invisible. We also do flashing services to de-Google other phone models on our store, as well as stocking pre-flashed pixels. We have a VPN service, Bytes VPN, which has features like Tor routing, DNS obfuscation, and ad blocking. We have Braxmail, which is a metadata-free way of doing email where no one knows where the message originated from. These products are on my app, BraxMe. Come visit us there. The link is in the description. Thank you for watching, and see you in the next video.